In this third video, we'll be looking at the answers to the questions posed in the previous video, and you will be able to check yours against those as we go through. For these even numbers after 2, which ones can be written as the sum of just 2 primes? The statement was every even number n greater than 2 is the sum of 2 primes. Did you think this is true or false? Well, it is termed the strong Goldbach conjecture, and it is not known whether it is true or false. It is suspected to be true, and hence it's called a conjecture, but it has not been proven to be the case for all n greater than 2. No one has found an even number n greater than 2 which is not the sum of 2 primes. If they did, then the statement would clearly be false. But on the other hand, no one has proven that you will always be able to find 2 primes whose sum is any even number that you give. The statement has been verified for n less than 4 times 10 to the 18. And it's also known that every even number n greater than 2 is the sum of at most 6 primes, but it's not been shown that it's the sum of 2 primes. For these odd numbers after 5, which ones can be written as the sum of just 3 primes? The statement was every odd number n greater than 5 is the sum of 3 primes. Did you think this is true or false? This is called the weak Goldbach conjecture. If the strong Goldbach conjecture is true, then the weak Goldbach conjecture will also be true, because if you take an odd number n greater than 5 and subtract 3, it will be an even number greater than 2. So if the strong Goldbach conjecture is true, that will be the sum of 2 primes p and q, and hence on rearrangement n will be 3 plus p plus q, so the sum of 3 primes. This statement's been verified for large n as shown, but in actual fact in 2013 a Peruvian mathematician has shown that the weak Goldbach conjecture is indeed true. And whilst he has not published this in a peer-reviewed paper, it's widely believed to be true based on his results. So in this case, I think we can safely assume that the weak Goldbach conjecture is true, well, so long as you believe his proof. For the numbers shown in the table, we ask the question, are there infinitely many twin prime pairs, primes that just differ by 2? Is this statement true or false? Well, it is not known whether there are infinitely many twin prime pairs, i.e. whether you will be able to continue finding more or there's a largest pair. So this is also a conjecture, thought to be true but not proven. What you will notice is that twin prime pairs straddle an even number, which is a multiple of 6. So for example, 11 and 13 have 12 in between, which is a multiple of 6, and 71 and 73 have 72 between, which is also a multiple of 6. For these even numbers, which ones are the difference of 2 consecutive primes? The statement was every even number is the difference of 2 consecutive primes. Did you put true or false? Well, again, it is not known whether this statement is true or not. It is believed to be true, but no one has proven it. There are other similar problems whether there are infinitely many pairs with gaps of, say, 4 or 6 and so on. But if you could manage to prove that there are infinitely many pairs with a prime gap of 2, you will have proved the twin prime conjecture. For these even numbers, which ones are the differences of any 2 primes? The statement was every even number is the difference of 2 primes. Is this true or false? Well, it is not known whether this is true or false either. So it's entirely possible that there is an even number which is not the difference of 2 primes. See if you could find one, and then you've disproved the statement, but no one has proven that it is true. And that's the statement that's believed to be true. These numbers that you will have calculated, which ones were prime? Well, in fact, they're all prime. You can see there are 5 numbers there that are all prime, that are all of the form 2 to the 2 to the n plus 1. What about the next one, 2 to the 2 to the 5 plus 1? Is that prime? Well, no, it has those 2 large factors. Similarly, the next one is also not prime. The statement said there are finitely many Fermat primes of that form. In other words, just the ones that you see at the top, the 5 given. Do you think there are any more? In which case the statement is false, or if you think those are the only ones, then the statement's true. Well, again, it is not known whether there are any more Fermat primes of that form. For these numbers, you will see that in most of them, but not all of them, we get prime numbers. So, for example, 2 squared minus 1 is prime, 2 cubed minus 1 is prime, 2 to the 5 minus 1 is prime, as is 2 to the 7 minus 1. But you notice that 2 to the 4 minus 1 is not, and 2 to the 6 minus 1 is not. One of those is 15, and the other one is 63. As shown. What about for higher powers? Well, you'll see there 2 to the 8 minus 1, 2 to the 9 minus 1, and 2 to the 10 minus 1 are all not prime. What about 2 to the 11 minus 1? Well, actually that's also not prime. The statement was there are infinitely many Mersenne primes of the form 2 to the n minus 1. So those are called Mersenne numbers, and if they're prime, they're called Mersenne primes. Do you think the statement is true or false? Well, again, it is not known whether there are infinitely many Mersenne primes of that form. And indeed, more continue to be found, but that doesn't prove that there's a largest one. Now, 2 to the n minus 1 is not prime when n is not prime. So there is no point looking for Mersenne primes of the form 2 to the n minus 1 and not checking with n being prime. N has to be prime for 2 to the n minus 1 to be prime, but that does not mean to say that if n is prime, 2 to the n minus 1 must be prime. Otherwise, we would know there are infinitely many Mersenne primes because we know there are infinitely many primes. So, for example, 2 to the 11 minus 1 is not prime, and yet 11 is prime. So, if the number n is not prime, it definitely will not be prime, but just because n is prime, it doesn't mean to say the Mersenne number is prime. What about 2 to the 13 minus 1? Well, that is in fact prime. Now, the largest prime found so far is indeed a Mersenne prime. Look at when it was discovered. It's the number shown, and it's got over 24 million digits. We mentioned that in the first video. These two graphs show the timeline for finding large primes, and not all large primes are Mersenne primes, but the larger ones tend to be Mersenne primes. There are primes of different kinds, and there are largest ones found so far. The bottom timeline shows you the rate at which the largest prime number has been found in terms of the number of digits, and you see the most recent one on the right hand side at the top. You'll also see on the top diagram the 51st largest Mersenne prime, which is the one I've just shown, and you see the 50th one just a bit smaller, found a little bit earlier. You'll also see that the ones that are the 47th and the 46th have been discovered in different orders. So the 46th one was found, and then sometime earlier than that there was actually a larger one found. So the 46th one, as you'll see, is displaced in position compared to the 47th one. You've calculated these numbers. Which ones of those are prime? Well, the first one with n equal 1 is, so 1 times 2 to the 1 plus 1, which is 3. But the next four shown are not. And in fact, the next one is with n equal 141. So 141 times 2 to the 141 plus 1. And it's quite a large number. The statement was that there are infinitely many primes of this form. They're called Cullen primes. Do you think that's true or false? Well, although we've shown the two with n equal 1 and n equal 141, it is not known whether there are infinitely many or finitely many. So this statement could be true or false. Similarly, calculating these numbers, we see that 7 and 23 are certainly prime. What about the next one after n equal 3? So the 23. So 63 is not prime and 159 is not prime. They're both divisible by 3. Well, the next one is with n equals 6. It's 383. And these are called Woodall primes of the form n to the 2n minus 1. Do you think there are infinitely many of that form? Do you think that's true or false? Well, again, it is not known whether there are infinitely many or finitely many, so it could be true or false. Calculating these, which are one more than a square number, we see that 2 and 5 and 17 are prime. What about with n equal 4? Which is 17. What's the next one? Well, with n equals 6, 6 squared plus 1 is the next one. Do you think there are infinitely many primes which are one more than a square number? True or false? Well, again, it is not known whether there's a largest prime of the form one more than a square number, or the list goes on forever and there are infinitely many. So it could be true or false. Calculating these numbers, again we see 2 and 5 are definitely prime. Four to the 4 plus 1, that's also prime. But 5 to the 5 plus 1 is not prime. Do you think there are finitely many primes of the form n to the n plus 1? So just the ones with n equal 1, n equal 2, and n equal 4. Do you think that's true or false? Well, again, it's not known whether there are finitely many primes of that form or infinitely many primes. So it could be either. Now, if n to the n plus 1 is a prime number, it's called a Sierpinski number, and it can be a Sierpinski prime. Then if that is prime, then n must be of the form 2 to the 2 to the k plus 1. So there's no point looking for any others other than the ones of that form. Looking at primes in gaps between squares of consecutive integers, between 1 squared and 2 squared there were 2 primes. Between 2 squared and 3 squared there are 2 primes. Between 3 squared and 4 squared there are also 2 primes. And between 4 squared and 5 squared there are 3. But then there are only 2. The statement was there is always at least 1 prime between n squared and n plus 1 squared. Now you might think because the gaps are getting larger, then you're always guaranteed to have at least 1 prime in the gap. On the other hand, the primes get rarer as you move through the list. So it's not clear whether this will be true or false. And in fact, it's not known whether it's true or false. So no squares of consecutive integers has not had a prime between them, but on the other hand, no one has proven that there will always be one. For question 13, we chose fractions, and we saw whether we could write any fraction as the ratio of 1 less than a prime p and 1 less than a prime q, with 2 examples. Is it true that any fraction of this form can always be written in that form? Do you think that's true or false? Well, again, it is not known whether this is always true or there are examples where it does not work, so it could be either. Similarly, for question 14, we're trying to write any fraction as the ratio of 1 more than 1 prime and 1 more than another prime. We gave examples. That was the statement. Do you think it's true or false? Well, it's not known whether it's true or false. Question 15. Consider 2 consecutive odd primes. So one's larger than 2. So the list on the bottom from 3 onwards. How many primes are there between those squares of consecutive primes? Between 3 squared and 5 squared, there are 5. Between 5 squared and 7 squared, there are 6. Between 7 squared and 11 squared, there are 15. Now here we haven't got the squares of consecutive numbers, we've got squares of consecutive primes. So the gap is bigger, and there are clearly more primes in that gap. The statement says there are always at least 4 primes between squares of consecutive odd primes. Do you think that's true or false? Well, it is not known whether it is true or false, so it remains a conjecture. Consider the difference of the square roots of two consecutive primes. For the primes 3 and 5, the difference of the square roots is 0.5041, which is less than 1, as it is for the next pair, less than 1, and so on. Do you think it's true that the difference between the square roots of two consecutive primes is always less than 1? Bearing in mind there are infinitely many primes, so you can't find them all, and there's not yet been found a formula which will give you all primes. So we do not know whether this statement is true or false. We considered which of the following numbers are prime. Well, 11 is, 111 is not, 1111 is not, and nor is 11,111. Now we note that the numbers above are all 1 less than a power of 10. But the only ones in the list shown at the top that are prime is just the first one. The next one is 19 digits long. It's 19 ones in a row, and it's of the form shown. And the next one is 23 digits long. What about the one after that? Well, that's 317 digits long, so the number with 317 ones in a row is also prime. But do you think there are infinitely many primes of that form? Or there's a largest one? Do you think that's true or false? Well, again, it is not known whether there are infinitely many or finitely many primes of that form. For the numbers shown, we asked which ones are prime. Well, whilst 101 is prime, 1001 is not, and 10,001 is not. These were primes of the form 1, 0, 0, and so on 1, so they're all 1 more than a power of 10. So of the ones shown, 101 is prime, the next two are not, and if you think that 11 is 1, 1 with no zeros in between, then 11 and 101 still form the same pattern. Are they the only primes? Are there only finitely many primes of the form 10 to the n plus 1? Do you think that's true or false? Well, again, it is not known if there are any other primes than 11 and 101. So a number beginning with 1 and ending with 1 and then zeros in between, or in the case with 11, no zeros in between. So for question 19, we considered the 4x4 and 6x6 tables, and we removed all the numbers which are not prime. And we observed in those two cases, every row had a prime, but not every column necessarily. The statement was that for all n by n squares, there's at least one prime in each row. Do you think that's true or false? Well, you can't check all squares of this kind because there are infinitely many, so you'd have to prove that there would be at least one prime in each row to say that this statement is true. And it's not known. There could be one which doesn't have a prime in a row. And lastly, for question 20, we considered squares of that form, which were of the form 3 by 3, 5 by 5, or any prime number times any prime number. So the next one will be 7 by 7. We removed all the primes, numbers which were not prime, and we saw that there's at least one prime in each row and each column. And the statement was that for any p by p square of this form, where p is prime, then there's at least one prime in each row and each column. Do you think that's true or false? Well, I hate to disappoint you, but again, it is not known whether this is true or false. So we're now going to move on to the final video, but in the meantime you can add up your numbers of trues and falses, and if you accept the Peruvian mathematician's proof of the weak Goldbach conjecture, then there should be at least one true in there, but of the remaining 19 they might all be true, or they might all be false, or they might be a mixture of true and false. It's believed that they are all true, but they all remain as conjectures. So if you've got numbers of true statements which are one or more, then you could have won.